The American Heritage Dictionary defines random as having no specific pattern, purpose, or objective. If scientists are correct that many natural processes are actually random, like the random mutations that form a fundamental part of the modern theory of evolution, or the inherent randomness of quantum mechanics, does this mean that nature is fundamentally without pattern, purpose, or objective? Is nature fundamentally disordered? We often consider order and randomness to be complete opposites. But when we look at some common examples, we can see them existing side by side. Imagine emptying your junk drawer into a big box, filling it with keys, expired coupons, pens and pencils, takeout menus, whatever. If you shake that box and look inside, you'll see a random collection of stuff bouncing around. If you stop shaking it, you'll see that same random collection of stuff sitting still. Now imagine dumping a bunch of ping pong balls into that same box and doing the same thing. If you shake the box and look inside, you'll still see a random chaotic mass. But if you stop shaking it, a very visible and specific hexagonal pattern will emerge. Both of these are random processes, very clearly so when they are in motion, but also in their end results. If we numbered the ping pong balls or painted them different colors, which ping pong ball ended up where would be unpredictable and random, even though the overall hexagonal pattern would always remain the same. How does this order arise out of randomness? The answer comes down to symmetry. Because the ping pong balls are all spheres of the same size, they tend to arrange themselves in the particular pattern we observed, known as hexagonal packing. From a physics perspective, this is just a process of minimizing gravitational energy as the motion stops. That is, of cramming as many of the ping pong balls as close to the bottom of the box as possible. This energy minimization process was also occurring in the previous example with the junk drawer box, but since its contents were all different shapes and sizes, no consistent obvious pattern emerged. It might seem like this nice hexagonal symmetry comes out of nowhere, some sudden order out of randomness. But if you look at it from the right perspective, you can see that we actually lost some symmetry in the process. Let me break this down for you. The hexagonal pattern is a six-fold symmetry, in the sense that there are 6 ways that I could rotate it and still get the same general pattern. It's a bit more complicated in 3 dimensions with lots of ping pong balls, but it is a finite symmetry. But each of the individual ping pong balls is a sphere, which could be rotated by any angle around any axis and look basically the same. The higher symmetry of the individual spheres, the infinite symmetry in this case, is broken down into a finite hexagonal pattern when they are all piled together. This sort of hexagonal packing shows up all over the place in nature. For example, you can think of honeycombs or the heads of certain flowers, or even a zoomed-in close-up of an insect eye. This pattern of higher symmetries breaking down to reveal new lower symmetries goes beyond simple geometry, though. In physics, there are complex mathematical symmetries at work in how we understand what electrons, quarks, and other fundamental particles are, and how they interact with one another. Those symmetries are, in a sense, broken down as these fundamental particles combine to form protons and neutrons and eventually atoms. But in doing so, they reveal lower symmetries of a kind that we find in the periodic table that are newer and in many ways more diverse. Those new symmetries are then broken down further as these atoms are arranged into molecules, revealing even more new patterns and shapes and symmetries of chemistry, and paving the way for the diversity and beauty that we find in the biological world. The motion and activity of the individual constituents are usually random and fairly unpredictable, but the patterns that emerge are usually very stable and extremely comprehensible. The biologist Stephen Jay Gould popularized a thought experiment of rewinding the tape of life, claiming that because of the randomness and variability of evolutionary biology, if we were able to rewind history hundreds of millions of years to some arbitrary point and let evolution run its course again, we would end up with a completely different taxonomy of life, different plants and animals. Now, apparently, some biologists contend that things might not be as different as Gould suggested, claiming that certain patterns and properties of animals and plants could be predicted to arise no matter what. But as a physicist, I'm more interested in the idea of running the tape of the universe back further and further, all the way to the Big Bang even. As best we can tell, right after the Big Bang happened, 13.8 billion years ago, the universe was a hot, dense quantum mess undergoing a chaotic explosion. If we were able to rerun the history of the universe from that moment, a great number of things about our universe would be very different. The Sun, the Earth, and the other planets of our solar system, and the rest of the Milky Way galaxy wouldn't exist as we know it. The particular distribution of stars and galaxies that form our universe and our familiar night sky would be redistributed as a result of random quantum fluctuations in the early universe. That being said, much about the structure and nature of the universe would remain exactly the same. The physical matter making up the universe would still be distributed into photons and electrons and quarks with exactly the same properties in roughly the same proportions, which would lead to similar distributions of protons and neutrons, and then the same distribution of atoms in the periodic table. While the particular location and distribution of stars and galaxies would vary, the general structure and history of those individual galaxies, stars, and even the planets would have unfolded much like our own universe did. It's fairly certain that even the properties of basic chemistry, like the formation of molecules like ammonia and water, and even some carbon-based organic chemistry like benzene rings, would have unfolded in just the same way. It is hotly debated whether life, as we know it or otherwise, would have necessarily developed in this rewound universe. Yet as unreliable as our biology textbooks might be in that universe, it's likely that our physics textbooks and large swaths of our chemistry textbooks would survive with only minor revisions. There are many processes in the natural world that are chaotic and random, at least in practice and most likely in principle as well. But this does not mean that the natural world is completely random, or that it is fundamentally disordered or unintelligible. In fact, randomness at one level often gives rise to order at a different level. And the way order seems to arise out of randomness in the natural world is almost always a sign of a deeper order and structure that we don't always notice at first. In fact, it is arguably precisely by giving up on the desire for complete order, stability, and predictability in every familiar physical process that scientists have actually come to a deeper understanding of the existing patterns and order present in nature. By letting go of the presumption that order and intelligibility would mean a sort of clockwork precision and predictability, we have not only come to understand significantly more profound truths about the order, structure, and causes present in our universe, we have also come one step closer to glimpsing the wonderful creativity of the God who established that order. For readings, podcasts, and more videos like this, go to Aquinas101.com. While you're there, be sure to sign up for one of our free video courses on Aquinas. And don't forget to like and share with your friends, because it matters what you think.